Okay. Thanks everyone for taking the time to come hear me talk. I want to tell you a little bit about what we've been doing at Horizon. Um, and essentially, the way we view quantum computing is quite different than the way most of the companies in the space focus on it. Um, we don't see quantum computing in quite the same way, and we see some of the problems that are faced on a path to large-scale quantum computing in a little bit different way too. And what I want to talk about is basically how we're trying to go from classical programming languages, from high-level languages like MATLAB or Python, all the way down to programs that are accelerated to run on quantum processors. And I want to start by saying, with computing. Computing has fundamentally changed the world. And part of that has been hardware. Without hardware, you don't have anything. But part of it's also software. And part of it is the software development tools that enable domain experts to make use of computers to solve hard problems. What it means to compute is starting to change. We're really at an early stage on a journey to more powerful computers. Now, quantum computers today, they're not powerful enough to really give an advantage on real-world problems, but that's starting to change. And quantum computing is a fundamentally new form of computation. It fundamentally generalizes what it means to compute. So how do we give programmers tools to actually take advantage of this new model of computation? When I think about quantum computers, I think of them as computers, not as special purpose devices for solving optimization problems, not as coprocessors for solving certain maths problems. And there's a reason for this. One of the reasons is that if you compare the timelines of classical computing to quantum computing, you see some striking comparisons. So a lot of the algorithms that were developed in the early days of conventional computing, say between about 1940 and 1960, have parallels today, well, between the early 1990s and today in quantum computing. And you could say, is this really a reflection of what these devices are good at solving? And I'd argue that no, it's not. Actually, it's a reflection of the type of people that are drawn to work on this kind of field. So the reason we see applications in cryptanalysis, the reason we see applications for simulating physical systems and for optimization are because these are problems that people who are drawn to work on quantum computing care about, just as people who were drawn to work on computing in the first place cared about those types of problems. We don't see applications that are very far removed from the domain of physics or computer science, where a lot of us who work in this space come from. Developing for quantum computers is fundamentally difficult. So how do you make the connection between the use case a user has and and a quantum solution to that problem? How do you write a quantum program that solves a user's problem in such a way that it's faster than anything that can be run on a conventional computer? There's really problems with this. First of all, quantum algorithms are really counterintuitive. So it's really difficult to construct a novel quantum algorithm from scratch. It's also the case that quantum hardware is extremely diverse at the moment, and it's very imperfect. So it's very noise prone, and you need to worry about mitigating those errors. You need to worry about fitting to a particular instruction set, to a particular connectivity, to the particular imperfections of a given device. And most quantum programming languages at the moment lack abstraction. So they're relatively low level. You're piecing together circuits gate by gate by gate, even if you're doing this in some Python framework. But imagine if things were different. And this is what we're thinking about. Imagine being able to go from classical code that's fast and efficient on conventional computers, say MATLAB code, for example, or Python code or Julia code or anything like that. Something that you can run on conventional computers, but being able to run it and accelerate it on quantum hardware. So imagine being able to give domain experts the tools they needed in order to be able to write applications that are faster on quantum processors without those domain experts having to become experts in quantum computing. And imagine being able to do this on all kinds of hardware. That's what we're shooting for, right? This is not the problem today. The hardware is still imperfect, but this is what we need to get to if quantum computing is really to take off, if we're really to get to a point where it's being used to solve real-world problems. So what we're trying to do at Horizon is to solve this problem by building up an abstraction layer so that we can sit between the users and the hardware. so that the users can program in an existing high-level programming language that can run on conventional hardware, but that can be compiled to run on quantum hardware, meaning that we automatically take care of the construction of quantum algorithms from that high-level classical code so that they take advantage of the quantum hardware and are more efficient when run on quantum hardware. Now, of course, the hardware is still a long way off, but there are hard software problems too that need to be solved in order to take advantage of that hardware. So what we've been building at Horizon is basically a tool chain. Go from purely classical code all the way down to a deployed application on quantum hardware that is accelerated by the hardware. And that works for any application. So whatever code you decide to write, we will automatically try to construct a quantum algorithm that achieves the same thing, but more efficiently. There's some examples where you can't do this. So if you have a string of bits, you want to compute the parity of them, that's not something where we're going to be able to find an advantage for you. But if you write code like most people, where there are loops and recursive function calls, that's something where we're very often able to find ways to accelerate the code on a quantum processor. And I want to talk to you a little bit today about two areas of the work we've been doing on this. The first is in terms of low-level programming. We've already got a toolchain working where we can compile quantum languages to basically any hardware in a way that takes into account characterization of that hardware. But we've started to augment that with the capability to compile C subroutines directly within the quantum code, so that you're able to write more complex quantum algorithms with less code. You're able to add further abstraction. You don't need to worry about how to implement the circuits to do these kinds of classical computations within your quantum subroutines. And then I want to talk about work we've been doing even higher up the stack in terms of automatically synthesizing quantum algorithms from conventional code. So in our case, we work with a subset of MATLAB code. In terms of the structure of the compiler we've been building, there's basically 4 layers to it. First of all, we're trying to automatically construct quantum algorithms from classical code. We're trying to turn it into a concrete circuit and then compile that down to the particular constraints and characterization of real hardware. But in order to do this, we've built up several different intermediate representations along the way. And we've essentially enabled code to be written directly in each one of these. So it's effectively a programming language. At the highest level, we're going from purely classical code. But as you go down, we have hydrogen and helium. Hydrogen is basically a gate-level language, and helium augments that with the flow control of BASIC. So this is an example of hydrogen. It looks pretty much like any other gate-level language, but one of the features of our language is that each of the operations you see here, from qubit to H, C0, measure, and so on, each one of these is not defined within our compiler. Instead, we load in a language file that tells the compiler what each of these quantum operations mean. And these are basically specified via their Krauss operators or via POVM elements. So this allows you to specify basically the most general possible quantum operation you could have, at least within some kind of Markovian assumption. So that makes it possible to deal with operations on any kind of hardware, whether you're talking about normal gates or whether you start talking about fusion operations and different things like this. We then augment that with the flow control of BASIC. So we have what are equivalent to numeric for loops. We have if statements, we have subroutines, and so on. And the reason to do this is to allow users to write somewhat more complex programs using reusable chunks of code, but also with less code, so that you're not expanding everything out. And we do it in this way rather than constructing it directly in Python as a complete circuit, because it allows us to do optimization directly on the program structure. What we've done now, our latest step with this, is we've added the ability to include C directly. So Helium already has the capability to include subroutines that are written in its own programming language, in Helium, but we can also now include files that are written in C. So this is an example on the left here. We're including a file, in this case an adder, that's written in C. So first of all, we include it at the top, and then as soon as we want to do addition, we just call go sub add, and that says we're gonna run that subroutine. Now, C, you don't generally write subroutines in it, you're writing functions instead. So we have this middle file here that we call a C2Q file, and basically it specifies how to take your C and turn it into a subroutine. So it tells you the file that it's being compiled from, tells you the entry point, the function that you want to enter within that C file, and it tells you what the arguments look like. But it also contains a number of flags that tell us what you care about in terms of optimization. Do you care about minimizing the number of qubits that are used, or do you care about minimizing depth or t-depth or something like this, some other metric? And the advantage of this is that it allows you to write really extremely complicated programs using relatively simple code. So you can go from C code to quantum circuits that would be unimaginable to try to create by hand. Oh, wow, okay, it's totally rescaled. We have a number of different modes within this. So you may have seen in the C2Q file there were different options to run different kinds of flags. Do I want to do the compilation using in-place linear operations? Do I want to try to reuse qubits to save qubits? And each of these can be flipped on and off. And we have a number of modes to tell us, do you want to minimize the depth or t-depth? Are you going to run this in an oracle where you're using it for Grover's algorithm or something like that, but you don't care about the phase? You only care about the actual effect on computational basis states, which is often the case if you're just going to use it to flag a qubit in a search, for example. And in that case, we get big savings in terms of the number of gates we need, because we don't actually implement the circuit you wrote. Instead, we just implement it up to phase, and that gives fairly big savings. So if we try to do this, if we actually run this on real code, do we get good results? And the answer is actually that we really do. There's a paper a little while ago from the quantum group at Goldman Sachs where they worked out gate counts for a particular derivatives pricing problem. And one of the most expensive operations in that was just implementing the exponential function. So implementing e to the minus x. So if you look at that, if you take the e to the minus x function, we can try to compile it using our system and compare that to different implementations that have appeared in the literature. So we've done this at a number of bits of precision, at 21-bit precision or 32-bit precision, which gives you about 10 to the minus 7 or 10 to the minus 9 precision on the result of that exponential. So if we do that for an input x in the range of 0 to 10, well, the method used in that original paper requires about 15,000 Toffoli gates. There's a more recent paper by Poirier, and it reduces that to about 1,600. And if we take that method, and instead of implementing it as a circuit, instead we just write some C code, about 15 lines of C, and compile it, it turns out we get a bit of an improvement. We get down to about 1,270 gates. But this is beating what you can construct by hand, and it's much easier. So you're writing a few lines of C code and getting to highly efficient circuits. But we get much bigger improvements than that. If we go to different ranges of x, so 0 to 100, for example, we're getting more like a 6.5-fold improvement, going from 912 Toffoli gates down to 140. And if we go to higher precision, so to 32 bits, for example, this kind of improvement holds up. You get similar kinds of improvement. So this is an automated compiler that is compiling just directly from C that's outperforming what you can piece together by hand. Okay, I wanted to show you a little bit of how the trade-offs in our system work. So we have different compiler modes. So in our C2Q file, if you change mode, if you set standard, it will do just the most simple thing. We first try to construct a classical circuit, and then we turn it into a reversible quantum circuit in a pretty standard way. But if we do in place, we'll try to use all of the linear operations in place, and that uses some heuristic algorithms to try to minimize the number of qubits that are used. But we also have an oracle mode and a low t-depth mode. And basically, the oracle mode, what it's trying to do it's trying to compute the same thing, but just up to the same phase. Sorry, up to phase. So it needs to do the correct permutation on the bits, but the phase doesn't matter. And the last one is low T-depth mode. So if you're trying to build a fault-tolerant quantum computer and you care about trying to solve a problem quickly, the deciding factor for you is probably the T-depth for the circuit. So how many layers of T-gates do you need? Because you need to do magic state distillation for each of these and so on. And if we do that, we can use different constructions on the way down, different optimization priorities, and we can get really dramatic improvements in, for example, T-depth, but at the cost of using extra qubits. Now, this is just some sample numbers for a particular problem that turns out to be a matrix multiplication, but the same is basically true in general. So if you're using the oracle mode, it's generally the best thing to do to minimize the number of T-gates or to minimize anything but depth. But once you want to minimize depth or T-depth, then there's specific constructions we use that burn a few more qubits, but that really reduce the depth. So in this case, there's a difference of between a T-depth of 240 and 11 in the best case and worst case. So this really allows you to set the priorities for what you care about. So do you care about making something that's really, really fast but uses a lot of qubits? Or do you care about something that uses as few qubits as possible and is still efficient but maybe a bit slower? Okay, so we've implemented that and we've been able to actually take code written in C, include it in Helium and compile directly all the way down and take the results of this, output it for whatever processor we want, all in one go, all in a continuous way, and then run that. And we've done it recently on the IonQ processor via AWS, but we're able to export for pretty much any hardware. So we've done our first runs now going from C, compiling it all the way down, and running essentially Grover's algorithm with a classical subroutine that was programmed in C, running directly on hardware and getting back good results. So in the case of this specific problem, we were computing the multiplicative inverse of a number modulo 4. So we were picking tree, finding what's the multiplicative inverse of tree mod 4, and using Grover's search to find it. Not really the best way you would want to approach this, but it's a nice little problem that actually fits on a real processor. I want to turn a little bit now to the other side of what we're doing in terms of the algorithm construction itself. And I want to give you a bit of a taste for how you can go from high-level classical code to something that is actually a quantum algorithm that outperforms that classical code. And this is a fairly complicated process, but there's basically two different things you need to care about. Generally, the runtime of some code that's been written isn't going to be determined by the number of lines in that program. Rather, it's going to be determined by how much code is reused, either because you go through it again and again with loops, or because you have recursive function calls, where a function calls itself or calls another function that calls it, and the whole thing telescopes out. So that's one kind of thing. That's one source of complexity in your program, and there's a number of ways we try to deal with that. But basically, what we try to do is when you have big loops, we try to pull them apart into smaller and smaller and smaller loops, simpler and simpler ones, but many, many loops. And this is usually the exact opposite of what optimizing compilers do. Most of the time, a conventional compiler will try to push loops together to eliminate branch conditions, for example. We're doing the opposite. But the reason we're breaking it down into these many, many different parts is so that we start to get simple building blocks that we can then recognize. So we have very simple loops that we can recognize, and they're always of one of some small number of different forms. And then we can replace that, ideally, with a more efficient algorithm for computing the same thing, but either exploiting quantum computing or exploiting classical preprocessing. The other side of things is you have operations that have high implicit cost. And that's one of the reasons that we've been focusing on MATLAB and Octave and languages like that. The reason for this is that a lot of the acceleration you can get comes about from matrix operations. So if you're doing matrix or tensor operations, you're for example, contracting tensors, or you're multiplying matrices, adding matrices, taking Kronecker products, taking Kronecker sums, doing all sorts of different things, computing determinants. These are things that you can speed up using quantum techniques. So in a lot of cases, this is using HHL-based techniques. But this gives you a way to get to very large speedups. So what we try to do is automatically apply these to classical code. So this is an example of an algorithm. It's written in MATLAB. You can copy and paste it into MATLAB, and you can run it. What it does is it takes as input some function f. It's just given by a function handle. And it takes as input also some range of the inputs of f, some lower bound on the range and some upper bound of the range. And we're going to assume that x is in some high dimensional space. So it's not a scalar input, instead it's some vector. And we also give in the dimensionality and then some argument that tells us how much we want to search for. But basically what this is going to do is it's going to search for the minimum value for f by first dividing up the space into a grid, searching each point on the grid, and finding the lowest value. And then around each one of those, we expand a finer grain grid and keep zooming in. So we keep finding the smallest value of the grid we're currently on, then expand around that at a finer grain and go in again. So this is just a kind of classical global optimization technique that you can run. And I want to show you this, how you can start to change this into a quantum algorithm. So the first thing we do is to eliminate intermediate variables that are defined within the code body. So for example, in this case, we have a variable called lattice points that's defined in terms of the inputs. So that gets eliminated. The next thing that happens is that because we have this definition for lattice points that's no longer used because we've substituted in the definition everywhere else in the code body, we can eliminate it. The next thing that happens is that this inner for loop, we try to split. We try to break it apart into simpler loops. So each of the variables in this were independent for one another, so they get broken apart. Okay. The next thing that happens is that we have some more intermediate variables that are defined within the code body and can be eliminated. The next thing we have now, there's some empty flow control that can also be eliminated. Now we have a single for loop that's inside, and this is an example of one of those simpler loops that I was telling you about. In this case, you can see that the loop, and I'm sorry about the indentation, it was different on my screen when I made these, but you can see that this inner loop is a very particular form where really what it's doing is it's defining a vector d, and it's defining the entries one at a time sequentially, starting with d equals 1 and then going up to d equals dim. In this case, we recognize that that's a particular function, and we break it apart. So we have a predefined function. In this case, you see it as column matrix definition. But we've recognized that that's what's happening. But because MATLAB is a little bit weird, we have to worry about the case, what happens when d, sorry, what happens when what happens when d is 0. So we add in this extra conditional to deal with that case. So where the loop goes 0 times, we know that d still needs to be set. It's either going to be set to the dimensionality or it's going to be set to 1, depending on whether that is 0, whether the loop enters 0 or more than 0 times. So we need to catch that particular case, because what we're really trying to do is construct code that behaves identically to your original code. We're trying to construct a quantum algorithm that does exactly what your code did. Not something vaguely similar, not something that maybe you could use in place of it, but that actually replicates the exact functionality of your code. So the next thing that happens, again, we have some intermediate variables that are defined but not used again, so they can be eliminated. In this case, we have a conditional if that can be removed. And then we get further down. We get to the lower part of the loop. We can see here x is used in several different places. And so it's defined. It's, again, an intermediate variable, but it's a function of the loop index m. So we split it out as a separate function, and then we can substitute in for it. So if we do that, now we can go back to the outer loop, and we can start to split this apart. And if we repeat this process again, we can look at this for loop. It's now in a simple form, and we can recognize that, again, it's a special case. In this case, it's a special case where x gets overwritten every time we pass through the loop. So we don't need a loop at all. We just need the final value of x. The next thing that happens is, again, we realize that this x is not being used anywhere else in the function. It's not an output, so it can get eliminated. And now we're on to the last loop. And again, this has a very particular structure. If you look at it, it has no effect unless the condition f is less than f min is satisfied. So we can replace this with a particular quantum routine that solves the same problem, but does it square root faster. So once we've done that, there's a little bit of final cleanup that needs to be done with some substitution and elimination of variables. And then we're replacing these special functions with quantum subroutines. So we're replacing these with pre-built quantum algorithms that solve those particular tasks. But we're going from general code and applying these in a way that's composable. So one thing adds to the next. OK, that's basically it for me, for what I wanted to show you. If you want to see some of this stuff actually in action, please drop by the booth, and you can see some of this happening on real code. The example I showed you just now with the MATLAB code, it's actually slightly different when you run it through the real system, because there's some cases that there's some subtleties to it I didn't explain in the talk. But come around, see us, and we can show you what happens in practice. If you're interested in trying any of this out, if you want to work with us, please sign up at the web page, horizonquantum.com, and you can register for early access. Thanks very much.
Thank you, Joe. We do have a couple of minutes for questions. Are there any questions up from the audience? And it's a little hard to see. We have a question over here. Might be a while. Could you go ahead and, all right, here comes the microphone. Stand by just a second.
Correct, and how do you for this process?
Sorry, sorry. How do we show it's correct? And
Well, how do you? Because you need to do some kind of quality control, right? When you do the program transformations, right?
Sure. So I mean, first of all, the transformed program you can still run classically. So you can substitute. Each of those functions is to do a particular thing. You can still run that. So if you're running classical code, you can run it before and after the transformation. So that's entirely possible. All of the transformations we're doing are built to preserve the functioning of the code. So it should never go to code that behaves in any way different from the original code. I'm sorry, I didn't catch that. Yes, exactly. So all of the transformations we can test individually, and the output code, again, if you make a small enough instance size that you can actually run it on a conventional computer, if you could run the original code, you can run the final code and compare.
So in the beginning of the talk, you mentioned that you're taking an approach called abstract approach, right? So how do you come up with that abstract approach? Like you fail doing traditional stuff? That's the question.
Oh, so I'm saying we're adding abstraction. So rather than focusing at the gate level, we try to build up higher and higher to get further and further away from focusing on individual gates. And the way we do that, we start with a gate level language. And
that's okay. The question is, why would you want to do that way?
Why would you want to do it? So there's an example, like a very simple example, is there's a fast matrix inversion algorithm that makes use of a rotation by an inverse arc sine. So you have some angle spent out in bits, and you want to rotate by that inverse arc sine. Can you write down the circuit for doing that? I mean, there's some research papers where people have tried to work out the best way to solve that one particular problem. It's a very simple calculation. You can type it into your laptop right now. You know, what's the, 1 over arc sine of whatever the number is. and it will easily give you the answer. But actually working out a circuit, even for that very simple operation, is really taxing. So we're focused on trying to make extremely efficient circuits for these things. Now, why would you want to go from classical code all the way down to try to construct a quantum algorithm for it, and then compile that all the way down? Well, the reason for doing that is pretty clear. There's not that many people that can make quantum algorithms, not meaningful ones, not non-trivial ones. And that's going to be a real bottleneck to use cases. Okay, yes, you could focus on QAOA and VQE and things like this, where you have a black box, you have a kind of black box solution for certain optimization tasks or certain chemistry tasks. But how are we going to tackle the wide variety of different applications that quantum computing can potentially help with? I'm not an expert in geophysics. I'm not sure how many people in this room are experts in geophysics, but computational geophysics is a big use case for high performance computing at the moment. How do we allow geophysicists working in oil and gas, for example, to be able to do those calculations faster? Because I'm not well placed. I don't think anyone here is well placed to tell them how to solve that problem. You need to construct a quantum algorithm for that task. And that means that someone that's skilled in the art of quantum algorithms needs to be able to first learn enough about computational geophysics to understand the problem, and then to try to work out a solution to it. So we're trying to automate that so that domain experts have the tools to be able to construct accelerated solutions directly.
If I can ask if we can hold follow-up questions to happy hour, because we do need to move on to the next speaker. So let's thank Joe for his talk.
Thanks very much.
Thank you.